Comes on everyone. Let's start off. Great. So last class, this is what we have done. We have started problems based on weighing machines. Are those cams on? Great. Let's go ahead with one more problem. Then we will continue with springs. We'll start off with springs today. Let's say we have an incline with a random surface. L is the length, H is the height. On this weird incline, you kept a rope. So this is a rope of linear density lambda. In school, right, you studied about density, which is mass per unit volume. Linear density is mass per unit length, meaning linear density in lambda kg per meter. Example, if someone tells you lambda is 3 kg per meter, the meaning of this thing is 1 meter rope has 3 kgs mass. So it's called linear density. The regular density is mass per unit volume. Others, if your cams are not on, I'll be removing you from the classroom. So we got a random rope here placed on a smooth incline. And this thing is some random surface completely. Height is h, length is l. That equation I have no idea. Now to keep this rope at rest, two people are pulling it. One guy is pulling here with tension T1, and here the other part tension is T2. So T1 and T2 are the tensions at the ends of the rope. Gravity is present, right? Find T1 minus T2 if the rope is at rest. How do you handle this? This is the first type of its model that we are doing, but you'll encounter this thing again, as you go on. You will see this again in friction and so on. But is everyone got the full picture what is happening? You got a rope. The rope ka shape, I don't know. It depends on that incline. Length, I don't know. I don't know the length of the rope. All that I know is the linear density, which is lambda kg per meter. Meaning 1 meter ka rope has a weight of lambda kg. So to keep this rope at rest, someone is pulling with T1 on the top and someone is pulling down with T2. What is the difference in tension T1 minus T2 if the rope is at rest?
Sir, why do we need to pull it from down to keep it at rest?
Let's say not required, but let's say someone is pulling. Someone attached a block or something. How do we proceed with this? Think, take a minute. If they ask a question like this in the exam, like again I'm saying, this is something I keep telling you. In the exam, what matters is getting the answer. Outside the exam, what matters is subject. So if you ask me something like this in the exam, you know what I will do? What do you think we should do? Frankly speaking, if I see the question for the first time, I have no idea what to do. I will look at this question and say, I will think like, what the hell is happening? That is the feeling I'll get because you didn't give me anything. It's some random shape, random rope. You gave everything there, and you're asking me find T1 minus T2. And that is the main advantage there. Look at this. That means it doesn't matter what is the shape of the rope, right? The answer should depend only on H and L. Isn't that what you're trying to tell me? You're telling me it doesn't matter what is the shape of the rope or what is the shape of that incline. The answer doesn't depend on the shape. That means, again, like I'm saying, for the purpose of the exam, then what I will do, I will take an incline. Then I will take a rope like this, which is just like a block here. Then this will be T1, this will be T2, and this weight will be mg sine theta. So I know T1 minus T2 is equal to mg sine theta. If this height is h, this hypotenuse will be h by sine theta. That is the length of the rope. So mass of the rope will be lambda into L, which will be lambda h by sine theta. I'll substitute here. I will get T1 minus T2 is equal to lambda h by sine theta into g sine theta. Sine theta cancels. I'll get lambda hg. That's your answer. You're getting what I did? Since you told me it doesn't depend on the shape, then I will take whatever shape I want. I will take an incline because I know how to do that. I'll get the answer for the purpose of the exam. But how do we do this actually? So after the exam gets over, then you still have to figure it out. So listen carefully to this. So on this random incline, right, and draw a little smaller one. Let's say you're taking a small part of the rope. Take a small piece. So dm is the mass of small length ds. So this length is ds. So dm will be lambda, that is mass per unit length into length. What are the forces acting on this small piece? The forces acting on this small piece, there will be a tension T here, T plus dt. Tension here will be T, and here you'll have, I'll do one thing here, I'll just draw an FPD there. So on that small piece there, if I treat it like an FBD here, the forces will be tension, T. Tension will be T plus dt. So the upper string is pulling with a different tension, lower thing is pulling with a different tension. This will be dmg cos theta. Remember here, theta is variable. Theta is changing at every instant.
So why is it
And
dt?
patience, Ray. Have some patience. This will be dmg sine theta. So what is this dt here? Dt is the change in tension. So every time as you climb the rope, because of that small mass, the tension will keep changing. Is there any guarantee tension will remain same everywhere? There's no guarantee. So for a small change in ds, let the change in tension be dt. This is the change in tension due to ds. You can clearly see here, this dmg sine theta is increasing the tension by a small amount, isn't it? Yeah. So as you're climbing the incline, for every small, the dmg sine theta, the tension will keep increasing. Theta is the angle of inclination, which is changing at every point. Since the rope has a mass, this is not a massless rope. If it is a massless rope, then you can say tension is same everywhere. Here you have a rope with a mass, so the tension will change at every instant.
So can we say the dt part is balancing the BMG part?
अभी वही आएगा ना. So now if you try to balance the forces, because this piece is in equilibrium, we can say T plus dt will be equal to T plus dmg sine theta. So the dt is actually created because of this dmg sine theta. What happens to the dmg cos theta? The dmg cos theta will be balanced by the normal reaction. Any doubt so far? So basically this small piece here, you can treat this like an incline. So the ds can be treated like a small incline. Any doubts on this page? Please ask me. This idea is very important because tomorrow, whenever you see something is variable, there is a rope rotating, rope has a friction. This is how you always draw an FBD for a small piece. So you have drawn FBD for a small piece of the string. Let the length of the small piece be ds, right? How many forces are acting? Tension on the top, tension at the bottom, your gravity, and normal reaction. There are 4 forces. Any doubts on this picture? Any doubts on this page? Samyak, Rudransh, Ovia, Shaunak, Arya, Aditi, Sudiksha, Vanshika, Trishi, clear with this? Great. So once we got dt, so dt is dmg sine theta. And what is dm? dm is nothing but lambda into ds. So this will be lambda as ds sine theta. Now look at this small piece here that you have taken. This is theta. This was ds. This is the vertical direction dy, and this was your dx. So from here we get ds sine theta is nothing but dy. That means you get dt is equal to lambda g dy. So the change in tension depends only on the vertical distance and doesn't depend actually on the length of the wire. Now integrate on both sides dt. This will be lambda g integral dy. This will go from 0 to height h. This will go from t2 to t1. This will come t1 minus t2 is equal to lambda gh. Pretty nice result. It doesn't depend on the shape. So that is how you get the tension, independent of the shape. So let me write this in a more general form. Suppose if you have some path like this, and let's say someone gives you a rope of this sort. And the best thing about this result, right? It doesn't matter how the path is. So if you have a rope like this, again, it should be a uniform rope. That is only condition. So if you have a rope like this, which is lambda kg per meter, if this side the tension is T1 and if this side the tension is T2, and if this difference in height and if this height is h1, where h1 is the height of the left end and h2 is the height of the second end, the difference in tension T1 minus T2 will be lambda g, the difference in height. There. This is a more general result. This is independent of shape of the rope. It doesn't matter what kind of shape you take. It only depends on the vertical height. So basically, what you can do? You can replace this whole picture with a rope. This is T1. This is T2. And you can treat this height as h1 minus h2. Both of them will give the same answer. Is the derivation clear, everyone? So it doesn't depend on the shape of that thing. Let's see how they can frame a question on this. This itself is a question actually. Most people will see that rope and they'll get scared and they'll not go ahead with the question. Clear with this? Let's see a question. Let's say if I ask you a question like this. Let's say we have a fixed cylinder. Someone took a rope. So that is 90 degrees there. This is a rope of length L. And mass M. Gravity is there. So if you leave it like, and this is a smooth incline, smooth cylinder. If I leave it like this, do you think it will remain at rest? It will fall down. So you tied this with a rope to a wall. So you tied this with a string. Find tension in the string in equilibrium. The length of the rope is greater than the radius. Greater than pi r by 2. That is the radius of the cylinder. Find tension in the string. Is the picture clear, everyone? So we got a fixed cylinder, gravity is there. Someone took a rope of length L. So it is making a quarter circle here, and the remaining rope is hanging like this. It is a smooth cylinder. So if you leave it like this rope will not remain there. Rope will actually start sliding down. In order to keep it at rest, you tied a string here to keep it at rest. What is the tension in that string so that the rope is at rest? Is the picture clear, everyone? Anyone not convinced with the question, not clear with the question, please ask me. So how do we use the previous result? That difference in tension T1 minus T2 is lambda GH. Try, you got 2 minutes. Now, in case you don't know the result, we can still integrate this, but if you know the result, it saves your time.
So the result was lambda GH, right?
Yeah. M by L into I minus pi by 2. Okay, mgrl by L pi r by L. Let's see when I don't remember the answer. First, let's get few data points here. What is lambda? Mass per unit length. So total mass of the rope is L and length is L. That's your lambda. Next thing. So for this rope, I know how to use the result only for the ends. Right. So you can actually directly use this. Then what will be this length? What will be the tension here? This is your T2. This will be 0 because this is an open end. There's nothing there pulling you at the bottom. There's no weight, nothing. So remember, free ends have zero tension. So if I somehow can find this height, my job is done actually. Because then the formula result, what you got is T minus, if I take this as T1 and that is T2, T1 minus T2 is equal to lambda GH. T2 is 0 because there's nothing hanging at the bottom. So T1 is lambda GH. So how do you find that H? This length is radius R. And this circumference will be how much? The total length must be L. This must be L minus pi R by 2. Is that making sense? The total length of the rope is L. So see, this circumference here is pi R by 2 because it's a quarter circle. So pi R by 2 plus this must be L. So the length L hanging must be L minus pi R by 2. And this is nothing but radius R. Therefore, H will be R plus L minus pi R by 2. You're done. Therefore, tension T1 will be lambda G H, which is R plus L minus pi R by 2. Lambda is nothing but M by L. There, you get it pretty fast if you actually use the formula, or else you have to integrate and figure it out. What was the formula? T1 minus T2 is lambda GH, where H is the difference in the height between the two ends. So what is the difference in height? This end is here and this end is here. So this is the total height. And like I said, it doesn't matter what is the shape of the rope. Is this clear, everyone?
So won't the weight of the rope cause T2 to be non-zero?
Which one? Weight of the rope become?
Wouldn't the weight of the rope cause T2 to be non-zero?
Ne, socho na. If you say T2 is not 0, so if I cut it here, how do you find tension? Remember, we cut it. So if I cut it here, what is there here?
Okay, there is
Nothing.
nothing, right?
So whom are you pulling exactly?
So, but won't gravity pull it down and to
अरे
maintain
pull
the...
करने के लिए God to pull there should be something there. There should be an mg na. What is m of this part?
Oh, right. It's nothing.
Is this clear, everyone? Clear with these ropes? So imagine you don't know this result, then how will you do? Think about that and let me know if someone can get an idea there. Right. So remember this question, pretty good one. Again, we are going to encounter something like this in friction again. But the result is cool. It depends only on the height. It doesn't matter what is the shape of the string, what is the length, horizontal, nothing. That is there. Srihari, just now we discussed why T2 is 0. It's a free end. There is nothing here at the bottom to pull you. Is that the doubt? So gravity will act on vacuum. There should be a mass to gravity act, God. Srihari, there is no mass here. What gravity you're talking about?
सर वो रोप को खींचेगा।
रोप यहाँ पे है। क्वेश्चन इज यहाँ पे क्या है?
वो कुछ नहीं है।
So if that rope is there, if I put a block here M, then यहाँ पे tension mg होगा ना?
सही है
Because
सर,
M is
पर रोप,
0.
हाँ सर, पर रोप का भी मास है।
So God, you want to find the tension here,
Oh, yes, sir. It
right?
is
So
0.
what is there below that? There's nothing there to pull you down. This thing is pushing from the top, isn't it? That we don't care, na?
Yes, sir.
Next thing, springs. Quite an important thing, but here we are going to a part of it. Springs, especially, right? We study this extensively in a chapter called simple harmonic motion oscillations. There we do this pretty much, but let's see. So till now we handled with normal reactions and tensions. So what does spring do? A spring simply it opposes deformation. So basically, if you see in nature, right, every system opposes the deformation. Deformation meaning compression and elongation. So whenever you try to deform a spring, that is, you compress or elongate a spring, it generates restoring forces. Look at the word restoring, meaning these are the forces which will try to bring you back to the normal state. This is nothing but tension only. Which is proportional to its elongation. So this is a standard springs, which is proportional to elongation or compression. So a spring, how much force it generates will depend on how much you're stretching it or compressing it. So the symbol for a spring, right, is this, a small helix kind of thing. So we have few terminologies here. We call it K. K is called the spring constant. We'll talk about that. So this dotted line is your natural length. So what is the meaning of natural length? When you say natural length, that means there is no compression or no elongation. You are in a pretty natural state. There is no tension in you. There is no compression or no elongation. That is called as natural length. Now, if you take this spring and if you try to stretch it, so let's say if you pull the spring by X forward, the spring will pull you back. That's what a spring does. You pull it, it pulls you back. You push it pushes you back. So if you pull the spring will pull you back. Suppose if you push the spring inside, that is if you compress it, the spring pushes you back. You can notice here the force and the X are always in opposite direction. So this X is elongation. If you stretch more than natural length, it is called elongation. If you stretch less than the natural length, you say it is compressed. So this force is given by the force due to the spring is given by minus K X bar. There, this is the formula for a spring. This K is called spring constant and this minus sign indicates opposition. The spring does not like to get stretched or compressed. So whenever you try to do that, it will try to generate a force, it will fight back with you. That's what the minus sign indicates. The elongation and the force are always in opposite direction. You can clearly see in the picture here, X is forward, F is backward. X is left side, F is on the right side. They're always opposite. So if you push, it pushes back. If you pull, it pulls back. And this K here is called spring constant. So K tells you how strong the spring is. The physical significance of K is higher the value of K, more difficult to deform the spring. That is the physical meaning. We'll talk about that in a bit. Higher the K, more difficult to deform the spring. So whenever you think, what does this K actually mean? It is kind of like your inertia, resistance. More difficult to deform. Did you ever see if you ever see a local train or anything, under the train compartment, did you guys ever see those springs?
Yeah.
And don't worry about the notes, right? Focus on listening and understanding. You'll get the PDF. right? So if you ever seen a spring under the trains, right, those things will be this thick. That sprinkler rod will be this thick. Next time observe that. If you have not seen, look at under the train, right? You will see those springs. Those springs, if you look at them, they look like rods. So under these local trains, you have pretty big springs. We call them shock absorbers. Ever heard about them? You have it in your vehicles and everything. Shock absorbers are actually springs. So if you look at this Mumbai local trains, the springs are so thick. Early morning when the train is empty, they're completely open. Evening when the train is packed, you will see they literally get compressed. Yeah, obviously trains are loaded to the limit. Train capacity is 1500, 4500 people are inside. So the springs go to that. So this kk value, right? It depends on. So there, that is a formula there. You can note it down. The thing in the red box. So this kk value depends on the nature of the material. If you make a spring with plastic, if you make a spring with steel, steel spring is stronger. If you make a string, spring with a thick wire and a thin wire, the thicker wire is more stronger. So kk value depends on nature of the material and it depends on the geometrical dimensions. Any doubts on this page?
No, sir.
Next thing, combination of springs. What happens if you keep springs in series and parallel? Quite a useful thing. We are going to see this again later on in this thing, but for now, series. So if you keep two springs in series, K1 and K2, you can replace them with one spring, K equivalent. We want to replace with one spring. So when do you say two springs are in series? They should have same tension. Both the springs will have same tension because they're connected by the same wire here, but they'll have different elongations. So the final spring which you're replacing should have an elongation of x1 plus x2. So if this thing has an elongation of x1, this thing has an elongation of x2. So you're replacing with one spring whose elongation is x1 plus x2. Since the tension is same in all of them, K1 x1 is equal to K2 x2 must be equal to K equivalent x1 plus x2. You can simplify from here and you will see you will get 1 by K equivalent is nothing but 1 by K1 plus 1 by K2. This will be opposite of resistances, everyone. If you keep springs in series, they behave like resistances in parallel. So if you keep two springs together, they actually become weaker. There, that is a formula for series. And you can think of the reason also. Initially, when you're stretching the spring, right, if you have only one spring and you're having an elongation of 10 centimeter, all the 10 centimeter only one spring gives. But if you have two springs now, they will distribute among themselves. So each spring will stretch lesser. So the wires are not that deformed. So you'll have lesser stress. Clear with this? So if your springs in series will behave like resistances in parallel, the formulas are reverse. If you have springs in parallel, K1 and K2, you can replace this with one spring K equivalent. In this case, springs have same elongation. Tension will be different. So if you have same elongation, we call they are in parallel. In resistors, if you remember, right, series means same current, parallel meaning same potential difference. So K equivalent becomes K1 plus K2. There, the formulas are completely reverse of resistances. Clear this? So do remember the results, quite useful, comes a lot. We're going to encounter this thing in this chapter also. Combination of springs. So this series parallel thing which you are studying, right? This kind of concepts you will see at least around 6 times in physics. You will see it in springs, capacitors, resistors, inductors. We have a lot of things, bulbs and all. Next thing, cutting off springs. What happens if you cut a spring? Now we are going to derive this formula later on in some other chapter, but the spring constant K is given by YA by L. There is a formula like this. So if you take a spring here, this thing here is your area of cross section. So how strong the spring is will depend on the thickness of the wire. This Y is called Young's modulus. If you remember, there was a question like this in units and dimensions. Don't worry about Young's modulus. What it simply means is higher the Young's modulus, it's called Hooke's law. Higher the Young's modulus, more stronger the spring. For example, so Y tells you about the strength of the material. So Young's modulus of steel is greater than Young's modulus of plastic. So let's not worry about it for now. Just remember Y tells you about strength. So if you look at the formula here, K into L will be Y into A. So whenever you cut a spring, the material won't change. So Y depends on material. And the area of cross section doesn't change. So K into L remains constant. So whenever you cut a spring, K into L remains constant. Let me show you with an example. So if you have a spring here, let's say K and L. So you take a scissor and you cut it here into two pieces. Let's say this length is L by 3 and this length is 2L by 3. You constructed two springs. Let this be K1, L by 3. This will be K2, 2L by 3. So this formula says K into L is constant. So K into L is K1 L by 3. K1 becomes 3K. So whenever you cut a spring, it actually becomes stronger. Similarly, K into L is K2 into 2L by 3. K2 becomes 3K by 2. There. So cutting a spring makes it stronger actually. And the reason is this: when the spring is smaller and if you try to stretch it, the wire will stretch more, right? Because in order to compensate for it. So the wire will undergo more tension. Think of like this. Let's say you have a 1 meter long spring and you stretched it. Example, let's say elongation is also 1 meter. Means what? Each loop here will stretch 1 centimeter. Na? But let's say you make this spring only 10 centimeters. And now your stretching elongation is 1 meter. That means this each loop will stretch 10 centimeters. The wire will get stretched much more than a normal thing. So the spring suddenly becomes much harder to stretch. So for now, just take it like that. We have a chapter called elasticity. We will handle there in more detail. But for now, I'm more interested in this result here. K into L is constant. If you cut a spring, K into L will remain constant, where K is the spring constant and L is the length of the spring. Series and parallel. This much stuff you should know. Total 4 formulas, everyone. Springs may F is equal to minus Kx. Springs in series, 1 by K equivalent is 1 by K1 plus 1 by K2. Springs in parallel, K1 plus K2. When you cut a spring, K into L is constant. These are your 4 results. Any doubts on any particular part here? Please ask me. All clear with this? Any doubts, Srihari? Shaunak? Shreyansh? Shaurya? Pratyasha? Siddesh? Great. Let's see our question. Let's start with something easy. So we got a spring here. We got a block here. Let's say this is 2 kg. 3 kg. Let's say this K1 is 200 Newton per meter. This is K2, which is 300 Newton per meter. System is at rest. Find elongation in each spring. In equilibrium. It's an easy one. Okay, give me both the answers, na? Don't type 1, 1. Give me both. K1, K2. So X1, X2. Let's see. You can take GS10 for convenience. So how to do the first one? Free body diagram. Let this elongation be X1. Let this elongation be X2. I will take the 3 kg block. You can choose anything as a system. The gravity is pulling down 30 newtons. The spring is pulling up, which is K2 into X2. So X1, X2 are elongations. It is an equilibrium. So K2, X2 is equal to 30. So X2 will be 0.1 meters or 10 centimeters. Same thing. Now I can take this whole thing as one system. That is easy. Just to show you, I'll take 2 kg block as a system. Then this will be K1, X1. The upper spring is pulling up. Remember, springs are pulling because they're stretched. Your own weight 20 and the lower spring is pulling, which is K2, X2. You could have taken 2 and 3 together. That would have been easy. So K1, X1 is equal to 20 plus K2, X2. This would be 200 into X1 is equal to 50. X1 is equal to 1/4 of a meter. Clear with this? What about the second one? You're right, Shaurya. Right, Obya. Samyak, right. What about this weird contraption? We have 3 springs, 2K, 2K, then 2 springs and 1 spring. All are in natural length. So you took the block and you slowly moved it till equilibrium. What is equilibrium? When the net force is 0. Then how much distance did the block move? Try, you got a minute. I hope the first part was clear. What to do here? You can take the K equivalent. The first 3 springs are in parallel. If they're in parallel, what will you do? K1 plus K2 plus K3. So you can write this thing as the upper 3 springs can be treated as 2K by 3. Then the middle 2 springs are in parallel, can be treated as 2K. Then this spring is K. And then you have a block. These 3 springs are in series. So 1 by K equivalent will be 1 by K plus 1 by 2K plus 1 by 2K by 3. How much will this be? This will be 3 by 2K.
So why
plus
3?
Why 3 matlab? Sorry, that is 6K, na? They will add up, my mistake. 1 by 6K. How much is this? 3 by 2 plus 1 by 6. So that put again 3 there, 9 plus 2, 10 by 6. 5 by 3K. That means K equivalent is 3K by 5. Meaning you can replace this entire springs with one system and one block. So here the spring will be 3K by 5. Easy. Now you're saying when it reaches equilibrium. So what are the forces here? This will be K equivalent into X and this will be mg. So you're done. So you'll get it from there. So K equivalent X is equal to mg. 3K by 5 into X is equal to mg. Any doubts on this? All clear? Let's see one more. Any doubts on this combination of springs? These things are in parallel, so add them. These are in parallel, add them. Then these 3 are in series. Kind of like resistors, but the formulas are reversed. All clear with this? Anyone confused with this? Devanshi? Clear with this? Yashvi? Vedika?
Sir, are these really parallel?
What doubt you have? Why are they not parallel?
They look directly connected to me, that's why.
They look to you directly connected. These 3 things are connected to the ceiling. These are connected to a rod. They are connected to the same system. So where it is directly connected.
Yes, sir. Yes, sir.
Yeah. Next one. This is a good one. Right? Let's see. Let's say we have a spring between 2 ends. Spring constant is K and length is L. Initially at natural length. Then what you did, So we have a point here, A, that is in the middle of the spring. You attach some rod kind of thing here and you pulled it with force F. So that point A is pulled with force F. This distance is 0.2 L and this distance is 0.8 L. You're not pulling the spring at the end, you're pulling the spring in the middle. A point A on the spring is pulled by F till it reaches equilibrium. Find the distance moved by A. So in this process, how much will that point A move? Initially, point A is at 0.12 from the right end and 0.8 L from the left end. K is the spring constant and L is the length. Page 180, this one. Nice one. No, yeah, that's not the answer. I hope the question is clear. See, if I keep a spring like this and if I pull in the corner, it is fine. You know how to do that. F is kx and you're done. I'm not pulling in the corner. You have a spring, you caught it at the middle, and then you're pulling that part of the string. It's like someone is, catching your elbow and then pulling your hand. Anyone confused with the picture here? Please ask me. Think, take a minute or two. Mm, yeah, Ishwan. No, yeah, that is wrong. Right, Samyak. You have one answer. Think I'll give one more minute. Others, you have one answer. Let's see. So the thing is, this is acting like two different springs. Nee, Siddesh. See, when you pull the spring, the reason why you can't treat the whole thing as one spring is because messed up something here. So you have two parts of the spring. This will become K2 and the length becomes 0.2 L. This will become K1 and this is 0.8 L. So you have two different springs of different length. And look at this thing. When you pull this point at this side, A, the right side gets compressed and the left side gets elongated. The total spring is not in compression. Total spring is not in elongation. The right part of the spring is compressed. and the left part of the spring is elongated. So within the same spring, you have some elongation and some part is getting compressed. And we know K into L is constant. So K into L will be K1 into 0.8 L. So the left spring will behave like how much? That is 8 by 10, 5K by 4. K into L is K2 into 0.2 L. So K2 will be 5K. So you can treat this whole system like, you can just assume an imaginary block A. On the right side, you're connected with a spring K2, which is 5K. On the left side, you're connected with another spring, 5K by 4. There. So you can replace the whole system with two different springs. So we can treat the two parts as two different springs. So if you start pulling in the middle, this is the problem. You cannot treat directly at F is equal to Kx. Because when you're writing F is equal to Kx, you are assuming the whole spring is elongated or whole spring is compressed. So if the part of the spring is compressed and part of the spring is elongated, you have to separate them out. So let this block go by distance x till equilibrium. So if you're pulling to the x, what are the forces on the block? The right spring, because it got compressed, you have a force F, that's what you're pulling with. This spring will push you back 5kx. This spring is elongated, so it will pull you back with 5kx by 4. Is that making sense, everyone? The right side gets compressed, so this will push back. This thing pulls back. So both the springs are acting in the same direction. Since it is an equilibrium, acceleration is 0. So F must be 5kx plus 5k by 4x. This will be 25kx by 4. Therefore, the elongation will be 4f by 25k. Check. Is the logic clear, everyone? So this is where the second thing which I taught you will come into the picture, cutting off springs. If you start pulling the springs in the middle, you cannot use your regular formula F is equal to kx. Then you will need this. But is that convincing why you can't use the formula F is equal to kx? The whole spring is not elongated, not compressed. Some part is elongated, some part is compressed. So what am I supposed to take? Compression or elongation? That's confusing. So cut it there. Then it is clear. The right spring is compressed, left spring is elongated. I can treat them separately and finish it off. But the moment you cut the springs, the spring constant changes. So that's where the headache is. Any doubts on this? Pretty good question.
Sir, can you explain the last part again?
This part,
Yes, sir.
where did you get confused? If you push the block to the right, you push the block to the x, right, on the right hand side. You're pulling in the force F, na?
Right.
So what will happen? So this spring will get compressed by x. This spring will get elongated by x.
Hmm.
So what are the forces on the block? Force F, spring force, spring force.
Right.
So there are three forces and it is an equilibrium. Any other doubts on this? Great. Next thing. What does a spring balance measure? So this is how we show the symbol. Just like, a weighing machine measures normal reaction, but it shows mass. A spring balance, let's say this is 10 kg. A spring balance measures tension in the string. So basically, if you cut a spring balance, you can just remove the spring balance, put a string, find the tension. So that's what the spring balance also measures. It measures tension in the spring. but it shows tension by G. So it will find whatever is the tension, it will divide by gravity G, and it will show that as the value. Are you clear with this? Spring balances measure tension, but they show you tension by G ka value, meaning they'll try to show you the mass if you have the tension is equal to mg. So we have 3 cases here. Ten kg and 10 kg. Find the reading of the spring balances in all the 3 cases. We have 3 cases. There are 3 spring balances. What will be the reading of the spring balances? Be careful. If I ask you a reading, you're finding tension by G. What you measure and what you show are 2 different things. Let's get this. So as long as you know how to find the tension, you'll be able to handle this. First case, you connect it to a wall and a block. Second case, there are 2 10 kg blocks. Third case, there is a 10 kg and a 5 kg block. What will be the reading of the spring balances? Give me all 3. Yeah, first 2 are easy. Third is the actual question. If I have to ask you this in mains, I'll ask you the third one. Neresh, man. What are you talking? So if I take you and tie you with 2 elephants on both the sides and pull you with equal force, you'll feel comfortable and relaxed. You should try that. Told you multiple times, tension is not net force. If 2 horses pull you with equal force on both the sides, you won't feel comfortable. Tension is something else. How do you find tension? You guys forgot. We wrote that steps also. Whenever you want to find tension, what we do? Step 1, assume the string is cut at a point where the tension has to be calculated. Now we get 2 parts. Draw the FBD of any one, then apply F is equal to MA. This is the process for finding tension. You have steps for literally everything that we did. Let's see the first 2. First 2 are easy. Both are 10 only. You won't get 0 in the second case. So how do you find tension? Draw the FBD. So this tension is T. This is 100. So tension will be 100. Here, if I draw the FBD, this is tension. This is 100. If I draw the tension, this is 100. Since both the sides is equal, acceleration is 0. Very confused. Tension is 100. That's it. That's how you find tension. I didn't ask you net force. Tell me one thing. Chalo, Ishmansi. If you think net force is 0, here wall is also pulling with tension T, right? This is also 100, na? Then that also should be 0. There is no difference between first and the second question. Right? The wall ka force is as good as this block. You remember this story, no? This was the story. The horse. So what is the reading in both the cases? The reading will be tension by G, which is 10 kg. So both the things will show 10 kg. What about the third one? 10 kg and 5 kg. Okay, Samyak got it. Question 3, nahi Utsa, that's not the answer. Right, ho gaya. Arya, you got tension. You are to supposed to say reading. By 10 divide karo na. Let's see. Let's see the third part. System won't be in equilibrium because the masses are unequal. This whole thing will start accelerating. So this is 5 kg. This is 10 kg. Let the tension be T. This is 50 newtons. Acceleration will be A up. This will be tension. This is kind of like that, Atwood machine, 100 and acceleration down. Write your equations. T minus 100 is equal to 10 into acceleration. T minus 50 net force is mass into acceleration. Up, positive, down, negative. Keep your sign convention simple. Divide them. You will get T minus 100 by T minus 50 is equal to minus 10A by 5A. That's minus 2. T is equal to 200 by 3. This is the tension. So what is the reading? Tension by G. So this will show 20 by 3 kg, 6.66. Clear with that? Yeah, I think most of you got it now. So remember, it doesn't show you the masses of the block, it shows the tension in the string. And if you put 10 and 5 kg unequal masses, it won't remain in equilibrium, it will start accelerating. So you have to find the tension like an Atwood machine. You could have actually used the Atwood machine formula. 2m1 m2g by m1 plus m2 would have got the same thing. But anyways, we are always drawn FBD. Clear with this? A decent mains level question. Any doubts on this? Take a break. Come back by 9:45. We'll continue from here. Take a 5-minute break. Any doubts so far? Chalo, come back in 5 minutes then. Sure, let's start off. I'm sorry, everyone. Next thing. So how does the strings and springs behave? So bit of a theory. So listen carefully. Tension in springs and strings. Now see, if you take a spring and let's say it is already hanging by mass m. So if you look at the spring here, what are the forces in equilibrium? The spring is pulling up with kx. You have your own weight mg. So we get x is equal to mg by k. Meaning if I have to show the picture more clear, let me do this. So this will be your natural length. Matlab, if there is no block here, the spring would have been here. This will be kx and this will be mg. This distance will be your elongation here, x will be mg by k. This is the scenario. Now what you did, you went and you took one more block here and you attached it. So we have a hook here, you took this block and you attached here. Now we want to see what happens immediately. The moment you attach the block, if you look at the spring doesn't care. It will, the blocks will become like this. Now look at the forces. This is mg. This will be mg. So weight has become double. But the spring will say, okay, from natural length, my elongation is still x. The spring will continue to exert same force. The kx will still be mg, but because of this reason, the blocks will start accelerating downward. So at that particular instant, the spring elongation will not change. Is that making sense? If you give little time, then the blocks will go down, then the spring will elongate. But instantaneously, at that instant, when you attach the block, the tension in the spring doesn't change. Because see, what is spring force? K into x. What is x? Elongation or compression. That's it. The spring force has nothing to do with the mg here. If you give some time, then it will stretch and then elongation will change and all that will happen. So when block is attached, the elongation doesn't change suddenly. It takes time. It does not change immediately. Right? Therefore, spring will continue to exert mg only. Is this clear, everyone? Spring doesn't care with how much force you pull it. Spring will only ask one question: what is my elongation or what is my compression? X. So K into X is my force. That's it. I don't care whether you pull with 100 or 2000 or 10,000 newtons. But if you give some time, then the blocks will move, spring will stretch, X will change, then spring force will change. Now, that's a different story. But at the instant when you keep the block, nothing is going to happen. Is this understood, everyone? This is what springs do. All clear with this? But same thing if you do with a string. Let's say we have a string here and we have a block M here with a hook. So at this instant, the tension will be T and this will be mg. If you attach a block, the moment you attach the block, understand a string cannot stretch or compress, nothing here. String cannot elongate in this case. The tension will suddenly change T dash. This will be mg and this will be mg. The acceleration has to be 0 since string cannot stretch. Tension suddenly becomes 2 mg. Tension can change instantaneously. You don't need any time. 0 time it will change. There. That is how tensions vary in springs and strings. In strings, you don't need any time delay. Immediately tension will change. In springs, it will depend on your elongation or compression. So it takes time. If you give time, then it will change. But at the moment when you attach the block, nothing is going to happen. Is this clear, everyone? A string and a spring. Next
Sir,
thing.
could you go back to the previous slide for 1 second? Yeah, okay.
All clear with this? Next thing. What if the spring has mass and springs are massless? Now, one thing. In our study, we take the springs to be massless. Generally, if nothing is mentioned, you always assume massless springs. So how does that make a difference? So see, if you have a massless spring, this is what happens. So if you have a massless spring, and the moment you cut somewhere, doesn't matter where you cut, because it has no mass, even if you apply a little force, there'll be infinite acceleration. That means the moment you cut it, it comes to natural length immediately. when a massless spring is cut, since it is massless, it has infinite acceleration. Its acceleration tends to infinity. Think of like this. When you say acceleration is equal to F by m, right? If m tends to 0, then this will tend to infinity, even for a small force. So therefore, it comes to a natural length instantaneously. So you have 0 time and you have an infinite acceleration. So that will come out to be a finite value. But again, in nature, you don't have any massless spring. This is hypothetical. And most of the things that we study will be this only, springs with without mass. What if you have a spring with mass? This we don't have it there in the portion, but just to have an idea. If you have a spring with mass, now there is an issue. Look at the picture here. So we have a block M here. Let's say this is your natural length. The moment you cut it at the top, now because the spring has some mass, there is a finite acceleration. And because there's a finite acceleration, it takes time for the spring to come. So this block will remain here. This spring is traveling. This point is coming down. The block will still remain here. The block won't move only for some time. So this point is coming down. This point is coming down. When this point comes to the natural length, now it starts moving. So here you'll have acceleration 0. Acceleration 0. Now it comes to natural length. Now it will start moving. Now this is what will happen. This will just fall with G. The spring comes to natural length and then the block starts moving. The problem when you have a mass, right? Each part of the coil or each part of the spring will have its own tension. Until unless the upper parts become 0, the lower part won't become 0. So it takes time for it to travel. Won't move unless spring comes to a natural length. So you will find a delay. So that is how we deal with springs with mass and springs without mass. Generally, in our portion, we don't have springs with mass, but I have an idea just in case. Let me show you something. Can you see that? That is a slinky, if you have ever played with one. Slinky is like the spring kind of thing. So see, when he's leaving the spring, that thing, what is happening? Look at the bottom, the bottom doesn't move. Then it moves. They're trying this with a bigger spring. You can see, I hope you can see that it's a much bigger slinky there. Slinky is that thing which you can play around. I'm pretty sure you must be knowing what the slinky is. So there we got a big spring. So we are leaving it from the top. Just observe the lower part. It doesn't move till it comes to the natural length. They left it. Look at that. Upper part is moving. The lower part doesn't care. then it moves. This is what happens if springs have mass, which is in reality that's what is how they work. If you see from the bottom view, you can clearly see the bottom part doesn't move a thing. It's at rest.
Physically at the same location.
So there, that is there. I'll post that in the group. You can check it out. I hope you have seen this. This thing I posted in the group. It's first law. You have a sand on a bad hits, sand remains there. Inertia basically. Yeah, that's a little thing about the slinky thing. Clear with that? So if the springs don't have mass, they will just move instantaneously. But yeah, music is creepy. But if the springs have mass, they will take time. Is this understood, everyone? In our portion, we'll take springs are massless. So let's see some questions based on this. We got a spring here. Let this block be mass m. We got one more spring here. This block is 2m. System is at rest. Massless springs. System is at rest and there is a gravity. So this point is A. This point is B. Find the acceleration of the blocks. At the instant when it is cut at case 1, you're cutting at A. Case 2, you're cutting at B. Two different questions. If you cut the string at point A, find the acceleration of block M and 2M. Second question, if you cut at B, find the acceleration of block M and block 2M. Hope the question is clear. Think, take a minute, then I'll show you one model. Okay. So how do you solve this kind of questions? Let me show you one model. So listen to the steps. So step 1, find the tension in the strings. When they're in equilibrium, just find the tensions. Step 2, whichever spring you're cutting, that tension becomes 0. that we saw just now. Whichever string you cut, that tension becomes 0. And other strings are unaffected. Other springs are unaffected. See, remember, the spring force depends only on k into x. If x doesn't change, the spring doesn't matter. The other springs are unaffected. Step 3, use F is equal to ma. Clear with the steps. Now let's see the question. Step 1, find the tension in the springs. So here, this will be TB, which is 2 mg. This is TA, which is 3 mg, because it is balancing both the blocks. I hope that was clear. Now, when A is cut, let's do for A. So the moment you're cutting at A, TA becomes 0. Like I said, whichever string you cut, that tension will become 0. The other guy, TB, will remain same because that elongation is unaffected. Draw the FBD of block M. What are the forces? TA, which has become 0, your own weight, mg, the tension, TB, acceleration, downward. So this will be mg plus TB, which is 2 mg, is equal to mass into acceleration. So this acceleration will be 3g. So this block actually goes on with 3g. Same thing, if I write for the 2m block, what are the forces? TB, which is pulling up, which is 2 mg. Your own weight is also 2 mg. So acceleration of 2m is 0. Is that clear, everyone? The moment you cut at point A, the block M will move, but the block 2m does not know what happened at the top because this spring will not move immediately. It will take time. If you give a millisecond, then the upper block will move down, then the spring will compress, and then B also will move. But the question is at the instant when the string is cut. Any doubts on this? Same question when you do for B. If you're cutting at B, then TB becomes 0. TA will remain same. Draw the FBD of M. This will be TA, which is 3 mg. Your own weight mg. TB has become 0. So this acceleration of M will be 3 mg minus mg is equal to ma. A will be 2g. So this block will fly up with 2g. What about 2m? TB has become 0. You have your own weight 2 mg and you have acceleration. You will be freely falling down. 2 mg is equal to 2 ma. A is equal to g. Any doubts on this? Please ask me. They're pretty important models. Any confusion, anything that you're not clear, please ask. That's it. You just follow the steps. Step 1, find the tension in the springs. Whichever spring you're cutting, make that 0. The other spring doesn't care. Then draw the FBD of M separately and 2M separately. Net force is equal to mass into acceleration. All clear with this? Let's see one more like this. There, we have 3 blocks here. This is A, this is B, this is C. Find the acceleration of the blocks when the string is cut at A, B, C. 3 different questions. at the instant of cutting. Just after string is cut. If you take a small time interval, I can't find. So sprinkle lengths will change and whole thing will get messed up. Let's get this. Pratyasha, just your cam, can't see you. Rudransh, Utsa, Arya, cams. Just your cams, everyone. Make sure your faces are visible on the screen. Others do keep your cams on. Chalo, chalo, focus. Don't sleep. I give you a 5-minute break also. You guys can't get tired. How do we do this? Same story. Remember step 1, find the tension in the springs. Step 2, whichever spring you cut, that will become 0. If you cut a string, that tension will become 0. Then draw the individual FBDs of A3 blocks. Net forces, mass to acceleration. Try. I'll give you a minute more, then I'll show you part A. Then I'll give you 1 minute for each. Try. Everyone should try. It's okay to get a wrong answer, but everyone should try. Only block M. Okay. Step 1, let's find the tensions. So TC will be 3 mg because it is balancing only a 3 mg block. TB is 5 mg because it is blocking, balancing both of them. So you are cutting at A. So the moment you cut at A, tension at A becomes 0. So you're cutting here, everyone, at point A. So B and C are unaffected. So TB will be 5 mg. So they will continue to exert same force. TC will be 3 mg. So if you draw the FBD of block M, now remember this whole thing is the same tension. So this whole thing will have same tension. So here also it is TB only. It's the same string. So this block M is pulled up with TB, which is 5 mg. Your weight mg and tension TA becomes 0. So you're going up with acceleration A. So this will be 5 mg minus mg is ma. A is equal to 4g. Now if you take the 2m block, luckily here nothing changed. So TB was 5 mg. Your own weight was 2 mg. Your TC was 3 mg. So this will say nothing happened. So acceleration is 0. Same thing with 3m also. These tensions are unaffected. Those blocks will be at rest for a moment. Next moment they will move. At this instant, nothing. There is no acceleration. Clear what I did? Can you do for B also now? C is the tricky one. Let's see. I don't remember the answers. Even I need to check. Can you do for B and C? B is also. . Okay, let's see whether you got it right. Try. I'll give you a minute more, then I'll show you the B part. One thing I want to tell you, if you're cutting B, there is no guarantee TA will remain same. Do you remember? TA is not a spring, TA is a string. In a string, tension can change instantaneously. I hope you're getting it. If you cut a string, it will be 0. But if you don't cut a string, there is no guarantee it will remain constant. So you have to be careful when you're cutting at B. There is no guarantee TA will remain same as the previous one. Let me show you one. Look at this. When you're doing for B, so you're cutting at B there. So what about TA? I don't know. That is the thing you should say. You don't know because tension at A can change. Tension at B becomes 0. That I know because the moment you cut the string there, that has to be 0. TC will remain same because that is also spring. So the thing is, the springs will maintain tension, but the strings don't care. We don't know what happens to the string. Now let's see what happens. If you take block MK TB becomes 0. So there's no one pulling you up. The weight mg is pushing you down. The moment you push it down, the string becomes loose. TA becomes 0 instantaneously. Strings cannot push. If that had been a rod, it would have been a different story. Since string cannot push, the moment you try to, that mg comes down, immediately it becomes loose. It becomes slack. That's a technical word, or loose. Therefore, tension at A becomes 0. That means this thing will just fall with G. So the moment you cut at B, the block M will fall with G. If you draw the FBD of 2M, I hope that was convincing. So you have to be careful. String cut tension can change instantaneously. There is no requirement of time. So here TB is 0. Your own weight 2 mg. Your TC is also pulling down with 3 mg. This would be your acceleration. So you get A is equal to 5g. This guy is going down with 5g. The 3M doesn't know what happened yet. This tension will be 3 mg. This will be 3 mg. Acceleration of 3M is 0. So there, so answer is G down, 5G down, and 0. Anyone got that 5G thing? Nope. See where it went wrong. I think someone got Utsa got it. Right, Utsa? Can you do for the C part now? Yeah, Ishman, you also got it. Try. Now, same logic. Can you do the C part? Always remember, you don't know the tension in the string will remain constant. So you always have to put a question mark. You have to figure out.
Sir.
So you can play a lot of combinations here. You can put the spring there, string here, and all. But I think you got the basic idea there. Zero 3M. Let's see the same story. This time you're cutting at C. So TA, we don't know. TB will remain same. TC will be 0. Now, if I draw the FBD of M, TB is pulling with 5 mg. The weight is mg. So this block is trying to go up. But there is a string here, which will not let you go. So this will be 4 mg. This is the difference between this and the previous one. In the previous one, the block was trying to come down and the string could not support compression, so it became 0. But if I try to pull you up, the string has no problem. Since string cannot stretch, the block M will remain at rest. Strings can pull, they can't push you back. So TA becomes 4 mg. Elongate, block does not move. So if you take B FBD, this will be 5 mg. This will be 2 mg. TC has become 0. This is the acceleration of 2m. 5 mg minus 2 mg is equal to 2 ma. A will be 3g by 2. This guy goes up with 3g by 2. And for 3m, TC has become 0, so you will just fall with g. Check everyone. Yeah, right, Utsav. Mishman. Block M0, block 2M, it will actually go up. Check this case, everyone. Any confusion on this, please ask me. हाँ सम्यक.
सर वो बी वाले में बी का मतलब 2m का एक्सीलरेशन
हाँ.
सर वो 5/2 होना चाहिए ना क्योंकि मास 2m है और उसमें 5 mg लग रहा है
5 mg
बी
minus
वाले
2 mg.
नहीं बी वाले में मतलब बी जब कट किया था
B में here, okay. 5 mg. हाँ, सही बोल रहे हो. I did a mistake here. So this was 5 mg is equal to 2m into acceleration. Yeah, that was a mistake. You're right. I hope everyone got these things. Cutting of springs. Now you can play more combinations of this. You know, you can cut this, cut that, and all this. So this is the main idea there. Any doubts on this problem? All clear with this? Going ahead? Let's see this. We got a block here of mass m. You tied with two strings, theta and theta. So in this string, let the tension be T. Let this point be A. Find the tension T in the string before and after cutting at A. Find the tension in the right string just before and after cutting. So if you're cutting the left string, what is the tension just before and just after? It's a pretty good one. Let's see. Let's finish off. Last one for the day. That should have given you some energy. Okay. After, why it is not 0, right? The before cutting was easy. Draw an FBD. Tension. Tension. This was theta. This was theta. So the vertical components will be T sine theta and T sine theta. And this was mg. So 2T sine theta was mg. So this was the tension before cutting. mg by 2 sine theta. What happens after cutting? नहीं रे हो गया. That's not the answer. What happens after cutting? Think, you got a minute or two. Before was easy. Right हो गया. Let's see. Now see, this is a common mistake what people do. Just after cutting, this is a scenario. This will actually start swinging like a pendulum, isn't it? Once you cut the left string, this block M here, if you look at this motion, this point here will actually start going in a circular motion like this. You're getting it? And this is the most common mistake what people think. So this tension will be some T dash, the tension will change. This is theta. So if you look at the vertical component, this will be T dash sine theta. This will be mg. You're forgetting something. This block also has a vertical acceleration. Think about it. When it is going like a pendulum, isn't the block coming down also? The block is coming down also, and the block is going horizontally also. The block will have two accelerations, ax and ay. So the common mistake is this. People think T dash sine theta is equal to mg. No, T dash sine theta minus mg will be mass into acceleration. There is a vertical direction. Ay is not 0. And horizontal direction T dash cos theta is equal to max. There will be two accelerations. So this is the actual equations if you do it normally. So the common mistake is this. People think T dash sine theta is equal to mg. This is wrong. Clear with that? So how do you solve this faster? Like you can take ax and ay, that becomes long. Remember, you can always choose an x and y axis however you want. So there's a more convenient way to do. Choose along the string as x and y axis. So choose this as your x axis and this is your y axis. So once you take like this, I'm pretty sure acceleration in y direction is 0. So this will be your tension. This will be your mg. If this is your angle theta, this angle will be, that is theta, this is theta, this is 90 degrees, this is 90 minus theta. Wait, I'll do one thing, I'll put just a small bob there. This will be theta. This will be 90 minus theta. So look at the components. I hope everyone got the angles there. So what are the components? So in this direction, there is an acceleration Ay, which is 0. Why? String cannot stretch. Later on, we will see in circular motion, you can have acceleration, but for now, let's not get into it. This thing has only an acceleration Ax. Is that making sense? So whenever you cut a string, right, it behaves like a pendulum. You can only go in the tangential direction. Along the string, you cannot stretch. So yeah, you're done. So look at the forces. This is tension. This is mg's cos theta. This is mg's sin theta. Accelerations, I'm choosing this is y direction, which is 0. This is x direction. Apply the forces. So T minus mg sin theta is equal to 0. The tension is mg sin theta. And the acceleration Ax will be g cos theta. I didn't ask you that, but you can find. Is this clear, everyone? So before cutting, the tension was mg by 2 sin theta. After cutting, the tension becomes mg sin theta. Is this thing clear, everyone? Because this thing will actually swing like a pendulum. There is a vertical component. You cannot write T dash sin theta is equal to mg. That is a blunder. So what we do actually, we write the tension this way only, but we divide mg into components. So you divide the components along the string. That will become more convenient to solve. Clear with this? Any doubts on this? So definitely check out this problem. It's a pretty good one. There. So that would be the last one for the day. So next class, when we catch up, we are going to do something called pseudo force. Pseudo force is not really a great concept. In laws of motion, it is kind of useless, but it is pretty useful in circular motion. So, but still we are going to do a basic of that. Right. And so next class, when we catch up, we'll continue with that. We will do pseudo force, and mostly I think it will be done in the first half of the class. We'll start off with a new chapter, friction. Friction is another quite an important chapter, right? It looks like NLM only. The only difference is you'll put extra one more force. So if you have to put it in simple words, loss of motion is like plain dosa. Friction is like masala dosa. Circular motion is Mysore masala dosa. Matlab, in that same dosa, right? You're just adding more and more and more. But the base thing is NLM only. So you'll not find friction something different, but yeah, it's a little you just need to figure out about the force. So don't miss the introduction, quite an important thing. So next class we'll start off with friction also. We have done 51 questions, everyone. So please make sure to go through the notes. You have a lot of variety here itself, and then to start solving your material. Okay, with that we'll wrap up for the day, right? And do remember Thursday there's a test online, so do make sure to give it. So any doubts in the class notes, any other doubts, please stay back and ask, or else you're free to leave.